shall we start the second talk? The second speaker today is Professor Shunsuke Takagi, and the title is Deformations of KLT and SLC Singularities. So please start.
Yes, thank you very much. Thank you very much for giving me an opportunity to speak this seminar. Today, I would like to talk about deformation of singularity in the minimal model program. This is a joint work with Kenta Sato. And so today, we work over a field of complex numbers. And the first, so let me prepare setting. So we consider proper flat family, and at the moment, so I assume C is the smooth curve, and small c is the close point of C. Then following results are known. First result is due to NO feedback. They proved if special fiber is two-dimensional KLT, then so are general fiber. So two-dimensional KLT singularity are stable under small deformation. And next result is due to Ishii. So Ishii proved log canonical case. So if special fiber is two-dimensional log canonical, then so are general fibers. And she proved a higher dimensional case. So this is result A, and result B is so if we assume generic fiber, our eta is a generic point of C. So generic fiber is Q-Gorenstein. Under this assumption, if special fiber has only isolated log canonical singularity, then so do general fibers. So this holds in arbitrary dimension. So this is second result. And third result is due to Shefford-Baron-Collar. Shefford-Baron-Collar. So they proved semi-log canonical case. Assume total space is normal. In a previous result, so I mean, in a result of NO feedback or in a result of Ishii, total space X is automatically normal because special fiber is KLT or special fiber is log canonical, so which implies the fiber is special fiber is normal. And once fiber is normal, then total space is normal around that fiber. So basically, we can assume total space is normal, but semi-log canonical is not normal. So then let me assume that total space is normal in this case. And generic fiber is Q-Gorenstein. So under this assumption, if special fiber is two-dimensional semi-log canonical, then so are general fibers. Yeah, I don't explain the precise definition of semi-log canonical singularity, but roughly speaking, semi-log canonical means normalization is log canonical. Yeah, these are known results about the deformation of KLT singularity or semi-log canonical singularity, and before explaining our result, so let me give a few remarks about these results. Okay.
Excuse me, are there boundaries?
Sorry, could you say again?
Are there boundaries?
Yeah, we can prove the boundary case. Yeah, we can prove, but in their original paper, so they don't consider pairs. But yeah, actually, we can prove.
Thank you very much.
Okay, and yeah. So first remark is so you may expect even in higher dimension, if special fiber is KLT, then general fiber is also KLT. But this is not true. In higher dimension, so we cannot expect such things. So what I want to say is analog of, for example, the analog of NO-feedback result does not hold in a higher dimension. If you don't assume anything about generic fiber. So let me give an example. This example is essentially due to unrelaxing. First, let me consider 5-dimensional polynomial ring. So A, B, C, D, E. And so this is a polynomial ring. And we consider 2x3 matrix whose entry are elements of S, like this. A square plus E to the fifth, B, D, C, A square, and B square minus D. So this is a 2x3 matrix. And let I be a ideal generated by all 2x2 minors of M. So ideal generated by all 2 minors of M. And let me denote by X. X is defined by I, which is a closed subscheme of spec of S. A spec of S is equal to the 5-dimensional affine space. And we also consider Cartier divisor D defined by E. So this is a Cartier divisor in X. And then we can construct a flat family, following flat family, whose central fiber is isomorphic to D cross affine line, and other cross fiber are isomorphic to X for all T not equal to 0. So I forgot to say, so X is, our X is not, sorry, in this example, so X is not Kugelstein, but our D is two-dimensional KLT. So in particular, this is Kugelstein. So central fiber, special fiber is, this is a three-dimensional KLT, but other cross fiber are not Kugelstein. So so not Kugelstein means not KLT or not log canonical. So yeah, because of such example, so in higher dimension, we need to assume Kugelstein condition, and that's why Ishii, so for example, in the result of Ishii, she assumed that generic fiber is Kugelstein. Yeah, similarly in the result of Shepard-Baron collapse, so they also assumed generic fiber is Kugelstein. So yeah, let me assume the generic fiber is Kugelstein. Then my question is, what we can say if generic fiber is Kugelstein. So this is the topic of today's talk. And so I want to answer this question using the theory of non-Kugelstein singularity initiated by Dufresne and Haycon. And okay, and sorry, let me give one more remark. So one more remark is total space is not necessarily Kugelstein. So which means we cannot apply inverse adjunction. So in my setting, so if our curly X is Kugelstein, then so closed fiber is special fiber is just a Cartier divisor of total space. So then if special fiber has only KLT or log canonical singularity, then by invertible adjunction, total space is also KLT singularity or log canonical singularity around the fiber. So by invertible adjunction, but so in order to use invertible adjunction, so total space should be Kugelstein, but in our setting, so total space is not necessarily Kugelstein. We want to put condition on fibers, but we don't want to put any condition on total space. So then, yeah, this is a problem. Yeah, this makes the problem difficult. Okay, then, and so as I said, so I use the theory of non-Kugelstein singularity, the theory of non-Kugelstein singularity, which is initiated by Dufresne and Haycon. So let me quickly review their theory. Okay, so this is the introduction, and now let me review the theory of non-Kugelstein singularity. So my X is normal variety over C, and I consider proper birational morphism. With Y normal, and my D is a Bayes divisor on X, which is not necessarily Q Cartier. Then, so Dufresne and Haycon maybe not. Define the pullback of value divisor as follows. First, they define natural pullback of D. So natural pullback of D is the value divisor on Y such that corresponding sheaf is equal to the reflexive hull of the image of OX minus D. And so using this natural pullback, so they defined pullback of D as follows. So pullback of D is defined to be the limit and m goes to infinity, limit of natural pullback of MD divided by M. And actually this limit is equal to infimum. So this is the infimum of natural pullback of MD divided by M. And this becomes R value divisor on Y. So using this pullback of value divisor, Dufresne-Heycon defined two relative canonical divisors. So first one is K minus. K minus is defined to be a KY minus pullback of KX. And second one is K plus. K plus is equal to KY plus pullback of minus KX. Of course, if KX is Q Cartier, they coincide with each other. But since in our case, so KX is just value divisor, so they are in general, so they are different. And K plus, in general, K plus is bigger than or equal to K minus. And of course, so if KX is Q Cartier, then they are equal to usual relative canonical divisor. Okay. Okay, then following is the non-Q Gorenstein version of log canonical or KLT singularity due to Dufresne-Heycon and Kikyo-Urbinati. Dufresne-Heycon and Kikyo-Urbinati. So now I assumed my pi, this one, proper variation morphism is log resolution. So I assume pi is a log resolution. Then we say X is Dufresne-Heycon KLT or Dufresne-Heycon log canonical if K minus, a coefficient of K minus is greater than -1 or greater than or equal to -1. So this is a definition of Dufresne-Heycon KLT or Dufresne-Heycon log canonical singularity. And we also say X is variative variatively KLT or variatively log canonical if K plus, the quotient of K plus is greater than -1 or quotient of K plus is greater than or equal to -1. Then, so as I mentioned, in general, K plus is bigger than K minus. So therefore, different Heikon KLT is stronger than variatively KLT. So different Heikon KLT implies variative KLT. Of course, different Heikon LC implies variative LC. And actually, yeah, different Heikon KLT implies Koema-Kore, but variative KLT in general does not imply KLT. Variative KLT singularity is not necessarily Koema-Kore. So they are different. And different Heikon KLT or different Heikon log canonically is, in some sense, is a natural singularity because we have a following characterization. Different Heikon KLT or log canonical if and only if there exists an effective Q-Bay divisor such that Kx plus delta is Q Cartier, and the pair is KLT or log canonical. So adding some suitable boundary divisor, so the pair become KLT or log canonical in the classical sense. So yeah, so different Heikon actually proved this equivalence. So in this sense, different Heikon KLT or log canonical is a natural singularity, I think. But unfortunately, they are not stable under small deformation. Sorry, they are not stable under small deformation. Yeah, okay. So let me go back to my previous example, this one. In the previous example, so special fiber is three-dimensional KLT, and in particular, three-dimensional KLT in the classical sense. So in particular, this is different Heikon KLT. But unfortunately, general fiber is not different Heikon KLT in this example. So yeah, from deformation theoretic point of view, so different Heikon KLT or log canonical and does not behave well. So in this talk, let me focus on the other type of singularity. So I mean, variative KLT or variative log canonical singularity. Our first main result is the following. So this is due to Sato and myself. Let X be a normal variety, and D is a normal Cartier divisor. Normal Cartier divisor on X, then if D is variably KLT, then X is also variable KLT. So we can prove the kind of inversion adjunction for variable KLT singularity without Q-Gorenstein assumption. Then, as a corollary of this result, so we have a following application to the deformation problem. So let F be a proper flat morphism. And our B is smooth variety, but in this case, not necessarily one-dimensional. Not necessarily one-dimensional. And then if special fiber is variable KLT, then so is so are general fibers. Yeah, we can prove variable KLT singularity are stable under flat deformation, and this scheme is not necessarily one-dimensional. So in particular, if generic fiber is Q-Gorenstein, under this assumption, general fiber is Q-Gorenstein, so variable KLT became usual KLT. So under this assumption, if special fiber is KLT, then general fiber also KLT. Yeah, this is our first application. And once you accept above theorem, proof is quite easy because since our base scheme is smooth, then special fiber is a locally complete intersection. So yeah, base scheme is not one-dimensional. So special fiber is not necessarily divisor, but still this is a locally complete intersection. So if a special fiber is variable KLT, then so repeated use of theorem implies total spaces variable KLT around the fiber. And then we can prove general fiber is variable KLT. So once you accept theorem, the corollary is quite easy. And let me explain how to prove theorem. So by definition, variable KLT singularity is defined by K plus, and K plus is by definition, this is an infimum of ky plus natural product of minus mkx divided by m. We take this infimum, and let me denote this divisor by k plus m yx. And then and then this divisor is so much easier to understand. So then the quotient of this k plus m is greater than -1. This condition is equivalent to the following condition. For any delta is not effective. This delta is anti-effective. So this is anti-effective Q-Bayes divisor on X such that M times Kx plus delta. This is Cartier, and the pair X and delta is sub-KLT. Sub-KLT is basically the same as KLT, but in a classical definition, of KLT pair, so we assume boundary divisor is effective. But in this case, so our delta is anti-effective. And if you allow the divisor which is not effective, then sometimes we call it sub-KLT. Yeah, anyway, so yeah, so basically, so this is the same as KLT, and anyway, so k plus m, the condition k plus m is greater than -1. This condition is characterized, can be interpreted like this, and then this condition can be characterized in terms of multiplier ideal. And this multiplier ideal shift is equal to OX MKX. This condition is equivalent to this condition. And basically, this containment always holds. So essential part is, I mean, the other containment is essential. And yeah, just in case, so let me recall the definition of a multiplier ideal in this setting. My X is normal, and my A is a fractional ideal. We take a log resolution such that image of A is invertible. And then multiplier ideal of omega x a t. So t is an exponent, t is a positive real number. So this shift is defined to be the push forward of omega y minus round down of t times f. So this is the definition of our multiplier ideal. So then if x is variative KLT, then so this by definition this means k plus is greater than -1, and then this implies k plus m is greater than -1. But since k plus is infimum of k plus m. Converse is not true. Even if k plus m is greater than -1 for every m, since taking infimum, so k plus might be equal to -1. So therefore, this is converse is not true. So this is a problem, but there's a trick to avoid such problem. So then we use some perturbation trick. We take some Cartier divisor on X such that whose support contains non-Q-Gorenstein locus. Then we can prove X is variable KLT if and only if. So there exists a small positive number epsilon. There exists a small number epsilon such that k plus m minus product of epsilon gamma, epsilon times this divisor, product epsilon times this divisor. This guy is greater than -1 for any m. Yeah. Adding small divisor, so we can get the equivalence. And this condition, so as above, this condition can be characterized in terms of multiplier ideal, like this. So this multiplier ideal shift is equal to OX MKX. So, and using this characterization, so we get a theorem using a restriction theorem for multiplier ideal. So then, now let me show this statement. So my D is normal Cartier divisor, and I assume D is variative KLT. And I take gamma, this is a Cartier divisor on X such that which contains a singular locus of X and singular locus of G, so not G, singular locus of D. Then, so using this characterization, we apply this characterization to D, then we get a multiplier ideal of D with this fractional ideals. This is equal to OD MKD, but OD MKD contains OX MKX, image of OX MKX. We are working locally, and so sorry, I forgot to say so. Since problem is local, so I assume X is affine. Okay, anyway, so then we by this characterization, so we have a this containment, and maybe let me. Oh my gosh. sorry, let me write like this. Then this multiplier ideal sheaf is contained in the image of a multiplier ideal sheaf of X. So this multiplier ideal sheaf is contained in the j omega x or x minus gamma with exponent epsilon or x mkx with exponent 1 minus 1 over m. So this is a restriction theorem for multiplier ideal sheaf. And this restriction theorem also follows from Kawamata-Fiebeck vanishing. Anyway, so we have a discontainment. So, sorry, the image of this sheaf. So basically, so this containment tells us this ideal this sheaf is containing this sheaf after taking the image in OD, but then by easy observation and basically by Nakayama's lemma, we get a containment before taking image. Yeah, this is just a Nakayama's lemma. This is the easy consequence of Nakayama's lemma. Anyway, so we get this containment, but basically, so this containment, then we apply this characterization again. Opposite inclusion is this is always false. So we get an equality, and this equality implies by this characterization, X is variative KLT. So this is our strategy. Yeah, it may look complicated, but idea is quite simple. First, we characterize variative KLT singularity in terms of multiplier ideal, and then second, we use restriction theorem for multiplier ideals. That's it. So, okay, this is about KLT case. So next, let me explain about log canonical case. Again, so let me assume X is normal and D is normal Cartier divisor. If D is Q-Einstein log canonical, then X is variatively log canonical. So in a KLT case, we proved if D is variative KLT, then X is variative KLT. But in a log canonical case, so we need to assume D is Q-Einstein. Then X is variative log canonical. So this is just a technical difficulty, and I believe this inclusion holds without Q-Einstein assumption only. But yeah, this is my question. Does the theorem hold without a Q-Einstein assumption only? Yeah. Yeah, I believe this should be true, but I don't know how to prove this. Anyway, so, and we can we can also prove the semi-log canonical case. In that case, our D is just S2 and G1. G1 means Gorenstein in codimension 1. So instead of assuming normals, we assume that D is S2 and G1. Then if D is Q Gorenstein semi-log canonical, then X is variative log canonical. I assume the X itself is normal still. Okay. Then as a corollary of this result, so this theorem has the following application to the deformation problem. Now my F is a proper flat morphism. And now see the smooth curve. And if the first assumption is if special fiber is Q Gorenstein and log canonical, then general fiber are variative log canonical. Actually, if special fiber is semi-log canonical, Q Gorenstein semi-log canonical, then yeah, general fiber are variative log canonical. And the second assertion is second claim is if generic fiber is Q Gorenstein, then under the assumptions generic fiber is Q Gorenstein, then if special fiber is Q Gorenstein and log canonical or semi-log canonical in a classical sense, then so are general fibers. So let me go back to the first page. In the introduction, I explained Ishii proved under the assumption generic fiber is Q Gorenstein, if special fiber has only isolated log canonical singularity, then so do general fibers. Now we remove the condition singularity is isolated. So we exclude this condition. So this result gives the generalization of the result of Ishii. And the strategy of the proof is the more or less same as the KLT case. I don't explain the detail, but so let me explain big idea. First, characterize variative log canonical singularity in terms of variance of Fujino's non-LC ideal. Fujino introduced the notion of non-LC ideals, which define the non-LC locus, and he developed. So this is Fujino's non-LC ideal is has a similar theory to the theory of multiplier ideals, and but for our purpose, his non-LC ideal is not enough. So then we introduce a variant of Fujino's non-LC ideals, and using that ideal, we characterize variative log canonical singularity. This is step one. And step two, then use the restriction theorem. for non-LC ideas. So Fujino proved a restriction theorem for non-LC ideal, but our non-LC ideal is slightly different from Fujino's one. So we reproduce restriction theorem for our non-LC ideal, and using that restriction theorem, so we proved we proved this statement. So if Cartier divides Q-Gorenstein log canonical, then X is variative log canonical. Yes, and this restriction theorem basically follows from the vanishing theorem for LC singularity. In a KLT case, so we use restriction theorem for multiplier ideals, which follows from Kawamata-Fiebeck vanishing. And in the log canonical case, our restriction theorem follows from vanishing theorem for log canonical singularity, so which is due to Ambro and Fujino. Okay, then let me give one more remark. Sorry, let me give one more remark. And actually, so this statement, corollary 2, Cora proved actually after finishing this project, so we realized Cora proved the same result in his unpublished book. Cora proved corollary 2 in his unpublished book, but the proof is quite different. Using so log canonical modification. Log canonical modification of total space. He proved so under this assumption, generic fiber is Q-Gorenstein. He proved that total space has LC modification. This follows from the combination of the result of Heikon-Shu and Odaka-Shu. And so, but the existence of LC modification is highly non-trivial, and this is quite deep result. But anyway, using LC modification, so Cora proved the same result. Its existence follows from result of Heikon-Shu and maybe Odaka-Shu. But so our proof use only vanishing theorem for log canonical singularity. So maybe and Cora's proof heavily depends on the existence of LC modification. So I believe our proof has our proof is of independent interest. Anyway, okay. Let me stop here. Thank you very much.
Thank you very much, Takagi Sensei. So, any question or comment to this talk? So I have a question. So could you go back to page number maybe 4 on the this adjunction? inversion adjunction. So, so if we consider the pair, I mean the boundary. So in that case, maybe right-hand side should be the pair X. Plus something. Can you?
Yeah, we can actually prove. Yeah, we can consider variatively PLT paired, and yeah, we can prove if D is variative KLT, then the pair is variative PLT. Yeah, we can prove this, but yeah. So in order to avoid complicatedness, so I didn't explain the pair definition, but let me give one more remark. So inversion adjunction. So about inversion adjunction, variative KLT singularity behave well, but adjunction, they don't satisfy adjunction. So which means this is not true.
I see.
If pair is variatively PLT, even if pair is variative PLT, D is not necessarily variative KLT. So so this direction is okay for different Heikon KLT. So variatively KLT singularity has an advantage and disadvantage. So inversion adjunction is okay, but adjunction is not.
Thank you very much. So any other question or comments?
Why is it is called variative something?
Because I think this natural product is defined in some sense variative. So we look at the variation, and in order to define this wave divisor, so we look at the variation. And I guess actually, so this terminology is due to my student. So I'm different Heikon only defined this singularity, and Kicke and Urbinati defined this singularity, but they called this singularity as a KLT plus singularity. But I don't like this terminology because KLT plus sounds like stronger than different KLT singularity, but reality is different. So KLT different Heikon is stronger than KLT plus singularity. So I don't like this terminology. So then my student Yoshikawa so so give another name, so variatively KLT singularity.
So both DFH and both are variative.
Yeah, both are variative, yes, but yes, yes, but yes, both are variative, yes.
Okay, thank you very much.
So any other question? So if not, let's thank speakers.
どうもありがとうございます。